Hi, welcome everyone to this presentation. Today I'm Laura Quesada-Ganuza and I'll be presenting this paper titled Risk Assessment Methodologies to Safeguard Historic Urban Areas from the Effect of Climate Change. Thank you very much for coming. The main goal of this study is to analyze and represent the interaction between urban spaces and heat waves via a Geographic Information System, GIS, data, considering the vulnerability of historic areas both as urban systems and as heritage areas. To frame this approach, socioeconomic, cultural, governance, which includes services and resources, and physical, gathering tangible characteristics of all infrastructures, elements and buildings, aspects of the system will be taken into account to have a more holistic perspective. To this end, key performance indicators addressing relevant vulnerable elements of historic urban areas are identified for the development of a risk assessment methodology. Complementary, as a foundation for the risk assessment, a categorization of vulnerability to heat waves is proposed for both buildings and urban spaces. Here, the gathering and processing of data for the development of a GIS-based model in the historic area of Bilbao, in the Basque country, is going to be presented. This work aims to serve as a basis and reference for future holistic assessment of heat waves risk in historic urban areas. This presentation will be divided into 5 parts. The first one will gather an introduction to the subject and will explain the objective of the study. In the second one, we'll present the first step that have to be taken for a risk assessment methodology in this subject, especially the framework in which we'll be working and the methodological approach of this study. In the third part, key performance indicators for risk assessment to heat waves will be presented. In the fourth one, we'll show the categorization for historic urban areas. And in the fifth one, we'll present the application of both the key performance indicators and the categorization especially the categorization in the case study of Bilbao's historic area and the development of a GIS model for this goal. This part will be divided itself into 2 sections. The first one will be the presentation of the case study and the history and different areas that compose Bilbao's historic parts. And in the second part, we'll be presenting and showing how the GIS model for Bilbao was built and the results of this categorization via this model. As stated by the World Meteorological Organization, global warming increases with the 21st century being the warmest on record. The IPCC states that the global warming is causing an increase in the frequency and strength of extreme events, with heat waves being one of the main ones. It's also important to note that urban areas and their surroundings record some of the maximum temperatures. The impact of heat waves can adversely affect not only the health of urban residents, well-being and livelihoods, but also affects the urban ecosystems and infrastructures. There are certain urban characteristics that differentiate the city's response to the changing climate, namely low permeability of the soil, density of the population, higher concentration of productive activities, and the specific construction materials. Within cities, all quarters are the root of cultural identity and the sense of place, concentrating important economic assets that makes them very relevant. These historic urban areas have very specific characteristics that differentiate them when faced with changes in climate and extreme events. In conclusion, the risk that historic urban areas face with climate change and related extreme events and its assessment is a priority to guide future policy and research. The main objective of this paper is to develop the first step for the development of a holistic and multi-criteria methodology for risk assessment of historic urban areas toward heat waves and implement them in the case study of Bilbao. The future methodology should provide support for the prioritization of future adaptation actions, using a holistic perspective to identify vulnerabilities and risks in historic urban areas. This research has a multi-scalar approach that considers both the buildings and the urban spaces. The proposed indicators and characterization are taking into account all kinds of urban areas to promote the integration at city scale and not stay isolated as historical events. Vulnerability and risk assessment methodologies are founded onto the use of individual or composite indicators that generate information about non-measurable conditions to enable to compare differently measured data. The main stressor or hazard in this case are heat waves, that are characterized differently depending on the climate. When assessing heat waves in urban areas, the urban heat island phenomenon must be a primary consideration. This phenomenon shows how morphology of an urban area affects its shading and ventilation. The technical and characteristics of urban elements and materials and the type and distribution of green space also influence its intensity. Urban geometry and materials influence wind flow, energy absorption, and the ability of surfaces to release long-wave radiation back to space, causing the urban heat island effect. As previously mentioned, the indicators derive mainly from literature review, either from an urban perspective or weathering of historic materials. For a holistic approach, the assessment of every system needs to be addressed, distinguishing between social, economic, cultural, governance, and physical systems. For the present study, the workflow is proposed as follows. The first step is the collection of information to feed a multi-scale data model, which in turn provides a statistical overview of the historical area and feeds the sample building categorization process explained in section 4 of this paper. That composes the second step. The more complete information gathered during this process is the basis of the last and third step of the vulnerability and risk assessment. Therefore, this paper encompasses the two steps shown in this figure, the information gathering and the statistical analysis and categorization. As guided by the foundation set in the previous section of this paper, the characterization of the potential impacts of heat waves and the urban heat island on the systems that conform the historic urban area will result in the following indicators. The impact chain for this methodology will be, therefore, the result of the mentioned approach and its combination with the R5 framework from the IPCC, resulting in this impact change shown in this slide. With the climate change and heat wave being the main hazards, the exposure will be the location of the historic urban areas, with the main assets being buildings and the public space. The holistic perspective will be provided by addressing all of the systems within this urban area, which are the physical, cultural, socioeconomic, and environmental systems. Beginning with heat waves as the hazard, the main parameters for its categorization will be temperature, humidity, and sun exposure. The different variations in relative humidity can adversely affect traditional materials. Therefore, humidity cycles and shocks have to be considered. In the case of exposure, in regards to the buildings, sun exposure or exposure to shortwave radiation is the primary indicator. Hence, the number of daily hours during which the envelope is hit by solar radiations, along with the orientation of the buildings, results in the exposure to the different facades to the sun. In addition, the shading of the surrounding buildings have to be taken into consideration. In the case of open spaces, urban heat island indicators such as sky view factor, normalized difference vegetation index or NDVI have to be considered. The phenomenon known as urban canyon is determined mainly by the sky view factor, indicating the proportion of an urban space related to heat storage. Also, the NDVI uses satellite images to quantify the amount and quality of the vegetation. Along with these two indicators, tropospheric ozone levels and acoustic pollution appear in literature linked to heat. Literature indicates that conditions such as high temperature, intense solar radiations, and long sunshine hours, all specific meteorological characteristics linked to heat waves, can cause an increase in ozone levels, with high ozone levels being dangerous for human health. Regarding acoustic pollution, heat storage inside buildings can be higher in high noise street noise areas because of inhabitants tending to reduce ventilation with the goal of shielding themselves from the noise. This causes an worsening of the thermal comfort inside buildings. As mentioned in exposure, sensitivity indicators are divided also between buildings and open spaces. Sensitivity of the buildings is divided among four aspects: social, physical, economic, and cultural. The social sensitivity regarding the population is defined by age group and socioeconomic data. Physical sensitivity, on the other hand, is determined by the possible weathering of sensitive traditional material under heat waves conditions, linked to their construction date and style, and the thermal characteristics of these materials, that is, albedo and thermal diffusivity. In the case of the economic sensitivity, the indicators are based on the use of the buildings, considering either its productive use, let's say residential, public, etc., or its relevance to tourism. Cultural sensitivity is defined by the link of the building either to communal memories or to rituals or traditions, and also its protection level as heritage. As for the sensitivity of public spaces to heat waves, the indicators are divided among its physical characteristics, in this case albedo, and its use, its cultural value regarding it is linked to communal memories or rituals or traditions. Coping capacity indicators are divided between buildings and public space. For the assessment of social coping capacity within the buildings, healthcare access, distance to hospital and availability of hospital beds, and awareness of the population to the hazard, like the existence of emergency plans, are the main indicators, added to the accessibility, in this case, the existence of the elevator. In the case of public open spaces, accessibility for ambulances and firefighters is the main parameter considered. The step of categorization is very relevant in a risk assessment methodology when it comes to its replicability. When assessing a large and varied stock of elements, such as the one that conform an urban area, a statistical approach is a very good strategy, with the aim to describe all the assets using archetypes of sample assets. To categorize an area, the methodology will be, therefore, a statistical overview of the characteristics of both buildings and open spaces, starting from samples and then extrapolating these results to the elements of the same category, resulting in a complete vulnerability assessment for the historical area. For this goal, it's necessary to create a limited number of samples that are a representation of almost every element under assessment of the historic urban area, taking into consideration data availability. Considering the approach used for the development of the indicators, the categories will reflect the vulnerability of both buildings and public spaces to heat waves, considering their cultural value, use, social and constructive characteristics. Moreover, data should be as widely available as possible in order to build a replicable model. Depending on the size and homogeneity of the area represented, the threshold should be set between 2 and 5%. Following the groundwork set in the development of the indicators, building categorization will be divided between physical sensitivity, use, cultural value, and social sensitivity. Physical sensitivity will gather the correlation between the year of construction, divided into construction periods that have a similar construction techniques and material, and the state of conservation of the buildings. In the case of the use, mainly the main use of the building will be taken into consideration. Added relevant characteristics such as commercial use, the existence of touristic apartments in it, or the sensitivity of its use to heat wave conditions. In regards to the cultural value, the protection level of the buildings will be considered, and also if it's linked or not to communal memories or traditions. For social sensitivity, the population density will be the main category, added to the population older than 65 that lives in the building. For the categorization of the public space, cultural value and environmental and physical characteristics will be the main parameters. In the case of the physical sensitivity, it will consider three subdivisions, starting with the sky view factor to predict the possible street canyons, NDVI levels to measure the amount of vegetation and the albedo of these spaces. In regards to the cultural value, it would be taken into consideration the relevance of the space for the life in the area, namely the amount of commercial activity in the ground floor, and then adding if it's linked or not to communal memories or traditions. For the environmental characteristics, the density or scale of the space will be considered, distinguishing between main and secondary streets and adding the parameter of the existence of traffic or if it's only a pedestrian street or area. As mentioned in the beginning, the last section of this study will be the case study of Bilbao's old quarters and will show the development of the GIS model built for the application of the characterization process that we just presented. Just note that they are in the order from the oldest part of the city center, namely the sector 1 called 7 streets or Siete Calles, till the 6th one, named Sendeja e Palza, which was developed in the 19th century. The first section, Siete Calles, has a layout inherited from the 10th century. So all of this area is between the 10th century and the 19th century. This GIS model that we'll present has been completed for the case study of Bilbao with semantic information available from public data sources. The data has been worked into two different ways. Most of it has been collected from the Basque government geographical information database and processed to automatically include in the data model. Other data has been obtained either from satellite data, namely Copernicus, or through Urban Multiscale Environmental Prediction, UMEP, plugins for QGIS. In addition to this, the data for the spatial rehabilitation plan of the historical center of Bilbao, namely the protection status of the buildings, have been introduced manually. As for Bilbao, not all the data mentioned in the previous steps has been available. Hence, some of the parameters have been simplified. They were not available, the state of conservation of the buildings, the age of the residents, as well as both indicators for the cultural value of the public space. For this reason, in the case of the building, social and physical characterization has been combined to provide a more specific statistical overview of the buildings. As explained in the sections 2 of this paper, the workflow shown in this figure, first step is the collection of information and the building of a multi-scale data model, which in turn provides a statistical overview of the historical area and fits the sample building categorization process explained in section 4 of this paper. The results of this process are divided between buildings and public space following the different aspects mentioned before. previously mentioned, for the case study of Bilbao, the social and physical characterization has been combined. Therefore, the main parameters used for the characterization of the buildings in this area were the year of construction, divided into 5 categories, the protection level, which also encompasses 5 categories, population density, which has 4 levels, and the use of the building, divided between residential, industrial, social and cultural, touristic and commercial, and monument. Because of this analysis and its implementation in the GIS model, 10 categories have a representativeness over the threshold set in the previous section of the 2%. As shown in this table, most of the buildings are from the period between 1850 and 1920, with basic or typological protection, residential, and with low population density. These categories encompass the 25% of the buildings, with the ones having a basic and ambiental protection encompassing the 20% of the buildings. Therefore, these two categories have almost half of the buildings in the area. For the characterization of the public space, 4 indicators were taken into consideration regarding the information available. These were the sky view factor, divided into 4 sections, then DVI, that has 3 categories, the relevance of the space to the area, divided into 3 levels, and the amount of traffic or pollution for that street, which is divided into a pedestrian street or a street open to traffic. For this public space categorization, 8 categories compose near the 90% of the representativeness shown in this table, in which we are maintaining the threshold of the 2% minimum representativeness. The major 3 categories that gather most of the spaces are the one with low sky view factor that characterize the narrowest streets, with a low NDVI for the lack of green elements in those areas. As a conclusion, we'll say that even though climate change risk assessment is a very relevant and necessary topic for designing resilient cities, there is a very noticeable gap in knowledge regarding heat waves vulnerability assessment for historic areas. This study presents the first step for a development of a holistic and multi-criteria methodology for risk assessment of historic urban areas toward heat waves, displaying its application at the case study of Bilbao. The next step should be the identification of risk with a holistic perspective in order to develop a full methodology that could help the prioritization of future conservation and adaptation actions. This is the end of the presentation. Thank you very much for attending. And instead, I'm Leire Quesada-Ganuza from the University of the Basque Country, the Faculty of Engineering of Bilbao. Thank you very much.